So bounds of zeros of a polynomial. So there's a theorem in our textbook. I'm not going to read the theorem. You can go back and refer to it, but I'll point out some details about it. So my example problem is going to be this polynomial. It's the same one that's in your book, but I recently did with a student and I messed it all up because I forgot one particular thing, but I'm going to add it in right now. When we want to determine, so overview, we want to determine what the zeros are for this polynomial. And so we start out with a number line that has infinitely many values, of course, right? And when I say infinitely many values, I'm not just talking about the integers, because recall that just between the numbers 1 and 2, on the interval from 1 to 2, there are infinitely many values in between those two integers. Okay? So that is a little bit of a problem, right? Because if I just wanted to even just start guessing, there's an infinite number of values that I can guess just between 1 and 2. How am I going to get there? Now, the bounds of zeros only examine really or apply to integers. And first we're going to try to find the upper bound or an upper bound of the zeros of this polynomial. What do I mean by bounds? Really, it's just a short way to say boundary. So when I say boundary, I want to know that, for instance, let's say that my zeros are in between 3 and -7, wherever -7 be. So that if my zeros are in between here, I've eliminated everything to the right of 3 and everything to the left of -7. So I've significantly reduced the number of values. Yes, and I still have infinitely many, but again, this bounds situation is really just looking at the integers. So even if I had all of just the integers, I would have infinitely many. But now I've just reduced it down to -6 up to 2 by finding the lower bound of -7 and the upper bound of 3. So that's the idea. That's what we're trying to do, is reduce the number of values that we have to consider as potential zeros for our polynomial. So what do we want to do? We just want to simply choose a number. We could do p's over q's to figure out what potentially the numbers would extend to. And if I multiply 3 times 6, I'd get 18. So I know that of the real rational roots that I have, they're going to be less than 18 and greater than -18. So it doesn't really help us to try 20 because it's not going to reduce the number of real zeros. So it may make sense to maybe go halfway between those two and first test 9. So let's do that. So we're going to do synthetic division, and we're going to test to see if 9 is a root or 0 of this polynomial. Now here's the error that I made when I worked with this with one of your peers, a student, and I failed to put in the 0 terms, and I just went to town on it, and all the work was just wrong. So there's an x cubed term. There's no x squared term, so I must put a 0 in there, right? Minus 7x. And yes, I know that I'm writing the whole polynomial down instead of just the coefficients, because I'm going to make that idea clear for everyone else. And I see an error already here. So let's clear out that negative sign. Oof, that would have been bad. And yes, I see that I've written the whole thing out, but I just want to emphasize this 0 term and make sure that we're clear what that is. So in synthetic division, one of the advantages is that I don't have to write all the x's as long as I put 0 terms in. I only need to keep track of the coefficients. So I get to write these coefficients down as such, and then I can go ahead and proceed. So let me erase some of this stuff and proceed with synthetic division to test if 9 is an upper bound. Let's slide this up a little bit. Let's actually create a little more space down here. Drag the 9 up. And of course, synthetic division wise, I'm going to copy my 3 down. 3 times 9 is 27. 27 plus 0 is 27. 9 times 27 is, I don't know, 243. 243 plus the -7. Remember, I'm adding. That's the other advantage to synthetic division. The one disadvantage, or one of the disadvantages, is that You can only use this when you're working with a monic binomial or a monic linear factor. So any x minus k, where k is the root, meaning this one would have been x minus 9. If you have anything like x, if you're dividing by, for instance, x squared plus 3x, blah, 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 can't use synthetic division. All right? 243 plus a negative 7 is going to be 236. And I'm going to take 9 and multiply it times that and get 236 times 9 times 236. Come on, poop. 36. 6. And I get 2124. So 2124. And then add 6 and I get 2130. Now, the portion of this theorem that refers or is regarding the upper bound states that the number that we're going to test, the root, has to be positive. So an upper bound value, upper bound will be positive, is a positive integer that in synthetic division, I'm not using the same language necessarily, division, the bottom row, the bottom resulting row, let's say, row is all positive. So, is this bottom row all positive? The 3 is positive, the 27 is positive, the 236 is positive, the 2130 is positive. So 9 is an upper bound. So that means that, as I said with the number line, that means that our zeros of our polynomial are not going to be greater than 9. Not going to be greater than 9. So if I drew that little number line very quickly again, 0, 1, dot, 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 out to 9, I know now that my zeros are less than 9. Okay? But the question, and this is to clarify the idea of, we're not concerned about necessarily an upper bound, because guess what? If 9 is an upper bound, isn't 10, isn't 11, because all the zeros are less than 11. And in fact, all the zeros are less than 2062, right? It was just arbitrarily chosen. So knowing an upper bound is helpful, but not as helpful as we want it to be. And we can find another upper bound. Let's try 8. So if I stick 8 in there, we'll do some synthetic division again. And I'm going to do this quickly because I'm pretty confident 8 is going to work based on the numbers that that resulted. So 3 times 8 is 24. That's going to be 24. 8 times 24 is 160. 32, 192. Subtract 7 from that, and I get 185. And you can see that if I take 8, multiply it times 185, I get some very large positive number. Add 6, and it's a very large positive number. So 8 is also an upper bound. Okay? And so, to be clear, right now I'm not just looking for the upper bound, or an upper bound. I'm looking for the least upper bound. The lowest number, the least number, that is an upper bound. So I'm going to skip 7 and go to 6. We'll see what happens. 3 times 6 is 18. 18 plus 0 is 18. 6 times 18 is 60, 108. Subtract 7 is a 101. And I still get a very large number when I multiply this times 6 and add that. And so 6 is an upper bound as well. So I want to scrunch down even more. Now, if I had some more insight into what possibly this was, I would have chosen maybe 6 to start with, but I don't know. Let's go down to 3. That might be too far. We'll find out. 3 times 3 is 9. 9 plus 0 is 9. 3 times 9 is 27. Add a negative 7, and I get 20. And 3 is an upper bound. Perfect. So I just skipped 5 and 4. And let's see if 1 is an upper bound. We'll skip 2 and see if we can be more efficient. 3. 3 times 1 is 3. Bring the 3 down. 3 times 1 is 3. And 3, that's negative 4. Negative 4, and that's 2. But that's negative, so it's already out. So now we got to see if 2 is an upper bound. And if 2 is an upper bound, it will be our least upper bound. So bring down the 3. 2 times 3 is 6. 6. 2 times 6 is 12. 5. 2 times 5 is 10. 16. 6 is an upper bound. And because we tested 1 and 1 is not an upper bound, 2 is my least upper bound. Okay? So now I know all the zeros are less than 2. And so I took off half the numbers, and now I have another half. But there's still infinitely many. So let's try to sort out where the lower bound is. And I'll try to tighten it up a little bit. So we're going to try to find the lower bound. And we don't care about all these upper bounds anymore. And so we want to actually think that 2 is the least. I'm going to abbreviate the least upper bound. So what do we want to try? I wish I had you in class. We could just ask you that and you guys could throw out a number. Let's try -3. And then we'll do the math and we'll sort out the criteria. So I'm going to bring down the 3. 3 times -3 is -9. -9 plus 0 is -9. -3 times -9 is 27 positive. Add to that a -7, and I get -20. -3 times -20 is 60. Add 6, and I get 66. I'm sorry, that's not a -20, you doofus. That's a positive 20. Positive, and this is negative, and so this is 54. I'm glad I caught that. I'm lucky I caught that. -54, as I said, didn't write. Now, for a number to be a lower bound, it's going to be an integer that when completed, I used a different word before, so if I was writing out the theorem, I would be consistent. When completing, or completed, I guess completing, synthetic division, the resulting bottom row is alternating in sign SIGN. So plus, minus, plus, minus, plus, minus, or minus, plus, minus, plus, minus, plus, doesn't matter. And this one, in fact, matches that, right? Here's plus, here's minus, here's plus, here's minus. The signs of our numbers in this bottom row are alternating. So we now know that -3, let's do it here, -3 is a lower bound. But again, not super helpful. I can't write lower. Is a lower bound. So not super helpful, just somewhat helpful. And it's because it's a lower bound. We now know that -4 is a lower bound, -72 is a lower bound, but we want to know the greatest lower bound. So what we want to know is the greatest lower bound. And I don't know that -3 is it yet. So I want the one that's as close to 0 as possible. So that's a question mark. I'm just setting it up to write in the number. So we're going to get closer. We're going to move up. And so we're going to try -2. Okay? So -2 is what we'll try next. We'll erase this definition stuff. And hopefully we'll run into the situation where I can talk about it, or I'll present the idea at the very end if we need. Okay? So we're going to get rid of all this stuff. And we're going to do this. And we're going to bring down the 3. -2 times 3 is -6. That's added, -6. -6. I don't know what I just did. 2 times negative. It seems like I did this before. Did I do this wrong before? I don't know. -2 times -6 is 12. And so that's going to be 5. -2 times 5 is 10. -10. No, okay, I was all right. I'm just misremembering the numbers, I think. -10 plus 6 is -4. And so is it alternating again? Yes. So -2 is also a bound. We don't know if it's the lowest, but it has the best chance. It's certainly, greatest. It certainly is in a better place than -3, so I'm going to replace it, and we'll go shoot for -1 and see what happens with the -1. Okay? Get rid of those, get rid of those. And we'll do the synthetic division with this. 3, -1 is -3, -3, -1 is 3, -4, and 1 times -4 is 4, and so that's 10, and it doesn't work, right? So -2 is my greatest lower bound. And that's it. Those are your bounds. Now, there's one particular situation that might happen. I'm not going to actually have an example for you. I'm just going to talk about it. So let's say we did the synthetic division. It's not going to turn out that way with the -1, but whatever it is, if we added and this came out to be 0, okay? Just let's say, as an example, not this problem, just talking about this. It came out to be 0, then this was a 7, and this was a -5, okay? Now, when we look at this, it doesn't look like it's alternating, right? Well, here's the thing. You can also, for the lower bound, not the upper bound, but for the lower bound, you can attribute a negative sign or a positive sign to the 0. The 0 does not have a sign. It's not negative or positive. But in this situation, 0 can count as the negative sign or positive sign depending on what else is going on. Not depending on. It can be either way no matter what. So you may want to say, oh, well, I'm going to treat this as a negative sign. Why? Because I want -1 to be my greatest lower bound. So this would alternate if we chose the negative sign for 0. So this would be a lower bound, if that was the case. It's not. I just inserted that, right? So that's the gist with upper and lower bounds of zeros of polynomials.